First, we're going to go over the geometry problems that we haven't seen in a while. The main problems that we looked at when we were talking about geometric applications were area problems and volume problems. And so on the first page of this review sheet, there are one of each. Well, I guess there's two of one of the other. In both cases, these have the extra work involved where we need to figure out the equation of the curves that are determining the regions, because they're not given, but they're all also just straight lines. So it's not a huge deal, but we do have to do it. The first line here, this diagonal line, goes through 0, 0, and 4, 2, which means that it has slope 1/2 and intercept 0. So if I were trying to find the equation of that line, it would just look like that. And this side goes through the 0.50 and also the 0.42. So we can tell from that the slope of that line is -2, and it has an x-intercept of 5. So this would be an easy way of writing that. -2 times x minus 5. That would be the equation of that line. It's easy to check that when x is 5, y is 0, and also that it has slope -2. So however you personally would like to find the equation of lines works just fine for this. The problem on the left, we're going to try to find an integral in terms of x, which means that we are talking about slicing the region vertically. So we have a generic slice at some x coordinate, and we're trying to find the area here. So we need to know the area of that slice. That slice is approximately a rectangle, and so and the width of it will be delta x, and then the height will be whatever is dictated by the y coordinates. The bottom y coordinate is 0, so that makes it easy. So all we really need to know is what's the y coordinate of this point at the top. So I'm just going to label this point up here. If the x coordinate is x, then we know the y coordinate is 1/2 x. And we know that because that point lies on the first line, and we found the equation of that line. So this rectangle has a height of 1/2 x and a width, well, and a width of delta x. So the total area I'm going to get by summing up those rectangles is 1/2 x. And notice that I only have that there because the bottom y coordinate is 0. So it's really the top y coordinate minus the bottom y coordinate. But in this case, that's just 1/2 x. And the width becomes dx. Now, the limits of integration are going to be over the possible x values. And that's where we realize that there's something funky going on with this problem, because that way that I just labeled the top coordinate would only applies to things that are to the left of the yellow line that I just drew. So that picture is only applicable for x's between 0 and 4. So if I sum up those rectangles from 0 to 4 using the integral, then that will give me the area of everything that's to the left of that yellow line. We also need to know what's going on to the right of the yellow line. And so I have another case over here where what if my x is bigger than 4? And when that happens, then the top point comes from the other equation, the equation of the other line. Again, the bottom y coordinate is still 0. And so I need to add to this the integral from 4 to 5, since that's where the values of x are. That would give me a rectangle of that form, of the top point minus the bottom point. So the top y coordinate is -2 times x minus 5. The bottom y coordinate is 0, and I'm summing those up between 4 and 5. So that integral that I wrote down is that, so the area of this thing with respect to x actually requires two different integrals, because the formula for the slices changes depending on whether your x is less than 4 or your x is greater than 4. So in this case, this problem was actually easier if we had sliced horizontally rather than vertically. If I slice this way, then the right-hand side of that slice is always on the steeper line, and the left-hand slice is always on the less steep line. So I don't have to have two integrals to find this area. I just need to find how to represent the area of one slice drawn this way, and then I can add that up for all possible values of y. The issue here, the reason we don't like these as much is because it forces us to work in terms of y. Let me just erase a little bit here so I have room. Okay. I'm going to label the points that are on the ends of this slice. The main thing to remember is that as soon as we make a horizontal slice, that means that the variable in my problem is going to be y, not x. And one way to think about that is that if you think about what information you need to know to decide where to draw that horizontal slice, the answer would be you need to know the y coordinate. If I said draw a horizontal slice at y equals 1, that tells you where to put that horizontal slice. If I said draw a horizontal slice at y equals 1.5, that would tell you where to draw that slice. So it's the value of y determines where the slice is, and so if I can figure out the area of one slice for whatever the y is, then I can just sum those up for all values of y between 0 and 2. Now, filling these things in requires that I have a formula for these curves that gives me the x-coordinate, that's what I need to know, in terms of the given y-coordinate. And the same thing here. The way we normally find that is by taking our normal equation and just solving it for x. This equation would be y equals 1/2 x, so it's very easy to just multiply both sides by 2, and it says x equals 2y. In other words, the point on the less steep curve has the property that the x-coordinate is always twice the y-coordinate. That's what the original equation says, and that's what writing it this way says. The other one was a little more complicated, and now I see that erasing it was kind of a mistake. If you remember, the equation as I wrote it was y equals -2 x minus 5. That's how I wrote that. So it's easy to think about the algebra solving this for x. Divide both sides by -2 and then add 5 to both sides. So that's going to give me an x-coordinate is -1/2 y plus 5. I'm going to write that 5 minus 1/2 y. When you're working with lines, don't forget that you can always just plug in points and check to see if your answer matches what you think it should be doing. And it's a good way to make sure you don't have things backwards. So for example, this point right here, that has a y-coordinate of 0, and this says 5 minus 0, which should be the x-coordinate, and that's what's happening. So when the y-coordinate is 0, the x-coordinate is 5, according to this. I can play the same game up here. When my y-coordinate is 2, then this says 5 minus 1/2 of 2, which is 4. My x-coordinate should be 4, and you can see that it is. So it's not hard to check that you have the right equation. So the advantage of going through that effort is that the area now is just the sum of all the rectangles I could get. Now the dimensions of that one slice rectangle, it's the height of the rectangle times the thickness. The height of the rectangle is just the difference in its x-coordinates. The y-coordinates are identical, so they don't really enter into it. It's the difference in the x-coordinates. And on the in the numbers, our number line, bigger numbers are to the right. If you forget that, look down at your axis, right? The bigger numbers are to the right. So if you're trying to measure a distance horizontally, you want to take the rightmost number minus the leftmost number. That will give you a positive distance between. And for my picture, I can see that the rightmost x-coordinate is this, and the leftmost x-coordinate is that. The thickness of that rectangle would be dy now instead of dx, and the y values should run from 0 to 2. So that's the easier integral, but it requires that we think about everything in terms of y. Okay, for a volume problem, the secret to doing a volume problem is to, first of all, think about, it requires some 3D visualization, but rather than think about the volume of this entire region being swept out and then slicing it, we learned that we could think of it instead as take a slice of the two-dimensional region and think about what happens when that one slice is revolved. So if you revolve that one stick about the x-axis, it'll look like a little disc. And most importantly, the radius of this disc comes from the height of that stick, exactly. So the volume of one slice is pi times the radius squared times the thickness. The thickness is going to be dx, or delta x, and the radius is just the height of that stick. And so knowing how high this is all I need to know to label that radius. And knowing that depends on where you slice. So if I label this top point, like I've been doing for the other problems, if I label the point on the curve that forms the outer edge of my disk, the x-coordinate will be called x, and the y-coordinate is going to come from the equation of this curve. This curve is a line going through 0, 0, and 10, 3, so it's going to have the equation y equals 3/10 x. So the radius of that slice is going to be 3/10 x. So pi times radius squared times thickness is the volume of one slice, and so the volume of the entire region is going to be the sum of all of those slices. So I'll have pi times 3/10 x squared dx, and the possible values of x for me, the places I could draw this slice, are anywhere from 0 up to 10. Now in this problem, it asks us to go ahead and evaluate that. If you are going to evaluate that, don't forget that everything that's a constant, which will be the pi and the 3/10 squared, so that's 9 over 100 pi, can all be pulled out in front because that's a constant, and we're really just integrating x squared from 0 to 100. So it's an easy power rule integral. I would encourage you to do it, and it's interesting to look up the formula from geometry for the volume of a cone, and you'll see that this is exactly what you would get. In fact, you could use this approach to prove that the volume of the cone formula is correct.